Okay, so recall we're in the middle of chapter 10, and this is all about how we can make alcohols, and so we're in the middle of handout 2, which is the reduction of carbonyls. And so we opened with the fact that to do a reduction of a carbonyl, we need nucleophilic hydrogens. Nucleophilic hydrogens. Nucleophilic hydrogens. These are hydrides, okay? And so the most common form of these hydrides are in NaBH4, or lithium aluminum hydride. And remember, I went through this really long mechanism, right? Where we have a good Lewis base. When the metal has 4 bonds to it, it's a good Lewis base. It wants to give up electrons, so it does so to the carbonyl and kicks up. And in doing so, we make this alkoxide, which is a pretty good nucleophile. Meanwhile, our metal is now a good Lewis acid. It's a good electrophile because it's only got 3 bonds. Remember I said it's never happy. So the nucleophile attacks the electrophile, and we get this structure, our Lewis acid Lewis base complex, which then again is still not happy. Now it wants to give up its electrons, so it delivers another hydride to another equivalent of the carbonyl. And again, it becomes a good Lewis base, so it gets attacked by the resulting alkoxide. And finally we get here, and this is where I was saying that we could keep going with these hydrides. They could, again, continue to be nucleophiles, because here we have 4 bonds on the metal. It's minus charged, got a formal negative charge, so it wants to be nucleophilic. But at this point, it's too unreactive. It's too bulky to react any further. Okay, so then this is where we work it up with water or with acid, whatever you want to do. We just protonate here one of our alcohols, which makes it a good leaving group. So when we have some base in solution, whoa, where did my minus charge go? If we have some base, it will come and kick it off. Okay, so it liberates our alcohol. This one will also get liberated, and we end up with this BOH2H2 negatively charged boron, and this just gets washed away in the workup again after this guy gets liberated. So I'm left off with saying that in theory all of those hydrides could be nucleophilic. Okay, again, so that would mean we only need 1 equivalent of the boron to every 4 equivalents of the carbonyl, because again, all 4 hydrides on the boron could be nucleophilic, so that's a 4-to-1. In reality though, like I was saying here, once it delivers 2 hydrides, okay, it becomes unreactive, and so only 2 will get delivered in reality, because then again, the metal becomes too unreactive. So then we would only need 1 equivalent of metal for every 2 equivalents of the carbonyl that we are reducing. But really in the lab, we just simply use 1-to-1, because we want an excess anyway, so we just use a 1-to-1 ratio. I told you guys to remind me that I had a funny story about this, so here it is. My experiment went completely and horribly wrong. I didn't get any product, and this is most likely due to the lab instructor telling me to use an excess of sodium borohydride to reduce my ketone. I was told to use a 1-to-1 ratio of sodium borohydride to my starting material ketone, and I didn't get any product. This is most likely due to this enormous amount of excess of sodium borohydride. It most likely ruined everything, and it is all the lab instructor's fault. So actually, your experiment went perfectly. Your NMR shows beautiful, clean product. You just couldn't read the NMR. The NMR shows beautiful, clean product. Your experiment worked perfectly. It did not go horribly wrong. You isolated beautiful, clean product. You just couldn't read the NMR. Nice job. Thanks, Ruby. Yes, so the moral of the story is 1, make sure you know how to read NMRs, and 2, never ever blame your lab instructor for what you think is a problem with the experiment, right? It's just not nice to blame the lab instructor. They're trying their best, and really, the lab instructor knows what they're doing. So, don't blame the lab instructor. Okay, anyway. Speaking of practical lab things, though, there is an important note that we need to make about these hydride reagents, okay? Important note. All right, and that is that the H- can also act as a base, right? Because every nucleophile has lone pairs that can also be basic. Okay, so obviously in most cases we don't want this, because we want our H- to be nucleophilic, but it can act as a base. So here's an example. Here's our lithium aluminum hydride reagent. Okay, Li+. If this comes into contact with any sort of alcohol like water, or any alcohol like methanol, what can happen is that instead of being nucleophilic, okay, it acts as a base. So these electrons will actually go and deprotonate that alcohol or water. We'll go and abstract that acidic proton, and then we make the infamous H2 gas, which is very scary because it is flammable. So we definitely don't want this to happen. Okay, so that's why whenever we run these reactions, we don't want acids. Acids in solution are bad. And so is water. We don't want water in these solutions, okay? Because again, we don't want this H2 gas. And there's a funny story. It's not really that funny, but when I was in graduate school, the lab above me did a reaction like this on like massive scale, I think on kilogram scale, and yep, they made some H2 because they had some water, and it caught fire and it blew up. So yes, beware. These hydrides can also be bases, and again, if they come into contact with any sort of alcohol or water, then they could blow up on you. Scary, fun times. So there are some differences between sodium borohydride and lithium aluminum hydride. Yes, the mechanism is the same, just a different metal, but they do have different reactivities, okay? So NABH4 reduces aldehydes to primary alcohols and ketones to secondary alcohols. But NABH4 is not a very strong reducing agent, okay? And so it is selective, okay? It does not react with more stable carbonyl groups such as esters or carboxylic acids, okay? So let's say we've got this aldehyde. NABH4. And so the most common solvent for NABH4 is ethanol. Okay, and I know that's an alcohol, but that's because of the solubility here is good, and NABH4 is not as reactive as the aluminum, so this will not take place as quickly, and it's not as scary. Okay, so the ROH is the common solvent. Common solvent with NABH4 because reacts with alcohols slowly and solubility is good. Okay, again, this was an aldehyde. And so when we throw in our sodium borohydride, what do we get? Just change that carbonyl into an alcohol. Okay? And so what degree of an alcohol is this? This is a primary alcohol. It's on a carbon that's bound to only one other carbon. It's a primary alcohol. Okay? Conversely, we start with a ketone. Okay? Ketone, again, we throw in some NABH4 in some methanol solvent. Okay, what do we get? Just change that carbonyl into an alcohol. And importantly here, what degree of an alcohol is this one? This is a secondary alcohol. Okay, so just depending on the starting material, again, you just put H2 across the double bond, it'll give you the product. Alright, but then importantly, as I mentioned about the selectivity, so let's say we've got this guy. What if we had two functionalities in there? Yes, you need to go back and review your functional groups because you need to know them. This is a ketone, and right here, here's our ester. Okay, when we throw in NABH4, it's a nice white powder. It's actually a really easy reaction. Again, with some methanol solvent, okay, what does it say up there? It's selective. It does not react with esters or carboxylic acids. So our product is only going to be the reduced ketone, and the ester is going to remain untouched. Okay, so we have no reaction at the ester. No reaction at ester. Just the alcohol has been reduced. Okay? And so, this is important. esters, carboxylic acids, and amides. Go back and review those functional groups. These are all very stable carbonyls, okay? Carbonyl functionalities are more stable, okay? And therefore, they're less reactive. So NABH4 doesn't react. They're less reactive than ketones and aldehydes. Okay. Why? Because of resonance. Lots of things are because of resonance, aren't they? So let's take an ester for example. Ester looks like this, right? It's got this lone pair on the OR group. So even carboxylic acids will have an OH, and amides have an N something here, have a nitrogen. Again, they all have lone pairs that can donate and kick up into the carbonyl. Okay, so we have these resonance, but again, you cannot do this with ketones or aldehydes. So that's why the ketones and aldehydes are more reactive than the esters, carboxylic acids, and amides. Okay, so again, we can't do with ketones and aldehydes. Right, importantly, we need this atom here with the lone pairs. You can see here we don't have anything like that over here to kick up into resonance. Only here. This resonance adds a greater amount of stability, and so the sodium borohydride is not strong enough to reduce these more stable carbonyl functionalities. Okay, whereas lithium aluminum hydride, however, is. Okay, it's a much stronger reducing agent, much stronger. So it easily reduces ketones and aldehydes, almost like very exothermically so, and it will also reduce the less reactive esters and carboxylic acids. And depending on your scale, it can also do that very exothermically as well. So that looks like this. When we think about the reduction, this is what reduction, I abbreviate it this way. If you go back to the section when I talked about the reduction of alkenes, I think I used this term, but by this I mean reduction. Reduction of esters. Here we go, looks like this. We have our ester. Again, this only works with lithium aluminum hydride. Yes, you can just write LAH, that's totally fine. But importantly then, we get a primary alcohol. So we've essentially added 3 H's, not just H2. But then we also have this OR group, and that becomes an alcohol. Okay, so everything pretty much gets reduced. So we're going to draw the mechanism. It will be a little bit steppy, but we should all have pretty good familiarity with it after drawing that big old long mech on Wednesday. Alright, so we have our hydride and our ester. And again, right, when it's in this form, it's a good Lewis base, so it wants to give up 2 electrons, so it does. Okay, the hydride is nucleophilic, it gets delivered. Again, start your arrow at that metal H bond, because it's those electrons that are getting delivered. Okay, and so, right, this gives us, it's not really an alkoxide, but it's equivalent to our alkoxide that we drew earlier. Okay, so now we have our H and our aluminum, right, which is now a good Lewis acid, right? It now wants electrons. Again, it's never happy, so it goes and accepts electrons from our nucleophilic O-. Okay, and this is where the mechanism gets a little bit different. O, A, L, H, H, H. Okay, so this is where before we would go and deliver another hydride to another carbonyl, but this OR group is actually somewhat unstable. So this OR group is actually a good leaving group in base. Is leaving group in basic solution. And since I just went over how basic these hydride reagents are, this is a basic solution. So what actually happens, instead of the hydride going and adding again, these electrons kick down and kicks off our leaving group. kicks off the OR. Okay, so this is where it gets a little bit different. And so we end up with an aldehyde first off. Okay, and with our aluminum still on there, ALH, H, H, and again we have kicked off our OR minus, which is actually an OK nucleophile, and so it can actually go and liberate the aluminum. Interesting. So now we have an aldehyde, and we have our aluminum. Importantly, he's got 4 bonds on him. Okay? And so importantly, when he's got 4 bonds, right, he is a good Lewis base or a good nucleophile. And we have our good electrophile here. This is actually more reactive than our starting material ester. This is an aldehyde. This is more reactive than starting material ester. Therefore, you can't stop it. It's going to get reduced again. Can't stop further reduction. You can't stop it. It's just going to happen. Okay? So, let's draw that. The hydride gets delivered. Okay? And now we have what's looking like our primary alcohol. Right? We have our alkoxide here now. And our aluminum, which is still never happy, because now it's a good Lewis acid. So it goes and gets attacked. I know it's a long mechanism. But now we are here. ALOR. And again, this is where it becomes too unreactive. And so I'm not going to keep drawing it the same. It's the same as before. Same as before. We have our workup. Right, the water will come in and protonate this guy, and then the OH minus will come in and liberate it off, just the same as before. And we get, after our workup, OH plus, this group is going to make an alcohol as well. HOR. Okay, same as before with workup. Okay, and importantly, here we get our key primary alcohol. Okay, so that's important. We do make a primary alcohol here as a result of this reduction. Okay, so let's look at a few examples. Okay, I know I don't have much room, but let's look at the selectivity. Let's use that same reagent, that same starting material we had before with the ketone and an ester. Alright, again we throw this in with some LAH. We will not use methanol for this reaction. Instead we use something called THF, and we have seen this before. This is what complexes with the borane to stabilize it. Okay, this is again not a proton, it is not a protic solvent. Okay, so the LAH again reacts with the protic solvents, reacts with ROH and other acidic protons violently. Therefore, no ROH or acidic protons, in the reaction. Okay, so again, here's our solvent. This is the more common solvent for LAH. It's the most common solvent. But importantly, right, it is a super strong reducing agent. Super strong. So we will reduce both the ketone and the ester. Okay, so both of them get reduced. So again, you just add H2 across there, and importantly, we've added kind of 3 H's across that carbonyl. Okay, how about this one? Again, we will highlight the selectivity. OCH3. Again, LAH with THF. Again, this is the solvent. Right? We get the primary alcohol. Sweet. Okay? We also get, HOCH3, just like we would over here. OCH3. It's just kind of like cut this right there and made an alcohol and two alcohols really. And importantly though too, right, if we do this same reaction with NaBH4, OCH3, NaBH4, importantly we will get no reaction. It's just going to sit there and stare at you because the NaBH4 is not strong enough. Sorry about that previous page being down there. Okay, it's just going to sit there. You can only reduce the esters with LAH. And so we have another really good example for you. I know I don't have room, so let's just go on to here really quick. Let's say we have this cyclic ester. This is known as a lactone. Here's a really good problem. You throw this guy in, let's throw in an aldehyde over here as well. Wow. Okay, we throw this guy in with some LAH. Everything's going to get reduced. So let's count our carbons. 1, 2, 3, 4, 5. Everything is going to get reduced. Okay, so we're going to reduce this guy. So this guy gets reduced to an alcohol. 3 is going to get reduced to an alcohol. And importantly, right, we have liberated the alcohol on carbon 5. Okay, 1, 2, 3, 4, 5. Wow. Okay, because again, the hydrides just get added here. It's going to kick up, and then eventually it's going to kick off this OR group. And that eventually becomes this alcohol when it kicks it off. Right? We learned this was the OR group. This is the leaving group in our basic solution. So once the hydride adds, it's going to kick up. Okay, so we can do this via I don't know. Let's say this guy's already been reduced because he's more reactive anyway. So he's in solution. So we have O minus over here, which can go and kick it off. Okay, to give O minus. And then here's our aldehyde, which again will go and get reduced. Okay, so yes, we get this crazy mess where we get everything gets reduced. Okay, so that's reduction. Good stuff. Synthesis of alcohols. Take carbonyl, reduce them. Yes.